standing waves, section 9.7. Ron, why don't you describe these are actually amplitude ripples caused by standing waves. Ron, you want to talk a little bit about that and some of the mechanisms?
We often call these things standing waves, but technically standing waves are a distribution of fields in a transmission line caused by one or more impedance mismatches, and that results in what we call amplitude ripple in the frequency domain. But we still call the amplitude ripple standing waves, but it's caused by standing waves. And when there's an impedance mismatch or impedance mismatches, the reflected waves interact with the incident waves inside the transmission line, the coax, and form the amplitude ripple that we see in the frequency domain. So when we see this, we've got to go out and figure out where those impedance mismatches are and get them corrected so we can have a nice flat frequency response again.
That's great. So there's a couple of different things. These standing waves can form pretty much anywhere in the distribution line, whether it be inside of the home or on a drop line or a hard line. James, do you want to talk a little bit about how you would differentiate between the two and where they're coming from?
Yeah. So, I mean, one of the things you're going to actually see in a couple of other videos, you're going to see examples of kind of like both of these. And to put a plug in for a paper that Ron worked on for the SCTE, the mathematics of cable. So one of the things you can actually do here, because we're looking at effectively an echo tunnel, if you take some measurements on the peak-to-peak characteristics of the wave there, it's actually going to give you, we can actually sort of do a calculation to tell us what the length of that echo tunnel is and that impedance mismatch is. So that's actually going to be another sort of like good way of sort of like understanding sort of like how long or where that sort of like impedance mismatch might actually be.
Nailed it. Brady, here's a trick question for you, not a trick for you, but a trick question. A common misconception about distances and locations and lengths is where it's from. Brady, are any of these distances ever measured from any location of any cable modem ever?
Never, ever are these distances measured from the back of the cable modem. So anytime we're talking about distances, we don't start at the back of the cable modem and walk to that where that impairment is. You're never going to find it that way.
Well said. It's so funny. Jason, talk a little bit about some of the work Cable Labs has done in characterizing these things.
Yeah, so one of the things we realize is that there's a lot of impairments in spectrum data that can kind of overlap, get rather confusing, hard to really look at. And while some of the examples we show here are pretty easy, some of these aren't so easy to figure out. So we're doing sort of self-training and doing some work with some data that allow us to also train some machine learning and anomaly detection solutions by having a lot of experts, some of those shown here and some others, to classify a lot of the data and use that to better identify these and create a database that we can use to train anomaly detectors too.
Right on. So I'll give you two simple little tricks here, and then we'll see the videos and it'll make a lot of sense. If you have a standing wave and it's at a single home or a single device and not shared by the neighbors, it's probably the drop cable. Start there and then possibly inside the home. Usually drop cables because they're most exposed to the environment. If you have multiple homes that share a standing wave, it should be pretty obvious that it's a common network problem, and you'll see it on a feeder line or taps, stuff like that. So we're going to show you both. Let's go ahead and Dean, let's roll to videos 1 and 2.
So we went to the input of the tap that was common to all those customers that had the standing wave, and this is what we found. The input connector on this tap was loose. There was also a kink in the cable and a squirrel chew. So we're going to go ahead and take care of these and then take another look. Okay, so here we've replaced the tap, replaced that input connector and re-spliced it. And now as we take a look at these customers' responses, the standing wave's gone.
In this example, we are going to look at a case where PNM full band capture shows a standing wave. As this impairment is not impacting any of the adjacent homes, we can be fairly sure the problem is going to be from the tap down to the home. Here, full band capture is identifying the standing wave as well as some FM interference. Looking at the spectrum trace, we can clearly see the standing wave impacting the entire downstream spectrum. This can be seen in both the RF trace as well as the channel power level trace. As this is isolated to just this one home, we know where to send the technician. So with that, let's see what we can find.
Okay, so I'm looking for a problem we detected in full band capture using the Occlusa tool from by James Medlock. So I came to an address and we're not seeing the wave that it was presenting that we're getting from the modem. So it looks fine here. I'm at the ground block, but I did notice a few things. I'm going to show you to it if I can. If you notice that, looks like there's been water and you see some oxidation on the center pin of the ground block. So yeah, that's pretty bad. So I'm thinking there's water in this drop, and then same with this. I'll show you this connector too. If I can get it off. This one here as well, you can see water damage, right? Rusting, corrosion. So I'm going to change out the connectors on both these, the input and output, this being the input obviously, and change out the ground block and go from there. So that's what I'm going to do right now, and then I'm going to go check the other end of the drop to see what we got. So as you can see here, we have the new connectors and a new ground block on. Okay, cable's clean, there's no water damage here. So I'm gonna go check the other end because I get a feeling that it's probably the same up at the top. Okay, so this is the drop I want. This one here. I'm gonna check that drop, see if it's what it's like, the connector. Oh yeah, this is bad. So no, it's pretty significant because you can see inside. You can see the corrosion. The dielectric around the center pin is all rusty color. Looks like there's a bit of water in there. Now, this looks like this was a pole transfer done a while back. As you can see, the drops aren't in really great shape. So, even though the full band capture at the side of the house shows that it's clean, I'm gonna get this put in to have these drops reinstalled. Okay, I don't know if you can see, but I cut back quite a bit actually, about 2 feet, almost 3 feet of this drop. And there's still a little bit of oxidization on the center pin. You can see that bit of green there. And no real discoloration of the dielectric. The outside jacket looks good, so I'm gonna put a connector on and then I'm gonna put it back on. Okay, so there we go, we have it. Just a couple notes to add. This looks like this was a recently new install. So I'm assuming that the installer that was here just brought the equipment inside, hooked it up and left. You know, and I understand sometimes they're in a hurry, but it's always good to take a few minutes out of your time, out of your day, just to go through some of the basics. In this case here, we had water and a ground block. Both connectors needed to be replaced, and the drop needs to be reinstalled, and there's also looks like there's water damage at the top here as well. So there you go, James, take it away.
Thanks, Arnie. So now let's see what PNM full band capture is reporting. As you can see, this home no longer shows that there being a standing wave, or in fact any FM interference. If we check the spectrum trace, we can now see a nice flat downstream spectrum, just as we would expect. And the previously reported FM interference is also gone as a result of the repair.
So but we do have a little bit of time. Gang, let's go reflect a little bit, no pun intended, on the standing wave. And then let's move on to the mystery impairment. And then that we should have a little bit of time to field questions from the field. So any comments on standing waves before we move on?
So Larry, I'd like to go ahead and promote the seminar that Kathy Fox did yesterday along with me. And she really focused on standing waves and water in particular in coax, and how important is the from a craftsmanship side of putting connectors on and all the different things that you can do to help prevent water ingress into coax cable, which I think Arnie was really focused on in James's video there. So, you know, if you keep the water out, you don't run into the problems of these water and coax that we saw with this particular standing wave example.
Yep. And one note about the standing wave is it was fairly periodic. So it looks like water was definitely in there because of the corrosion, but it may have dried up or run out because it didn't appear wet at the time. But that's part of the life cycle of water and cable is not a good thing. You're right about Kathy Fox's presentation. Absolutely killer. I would encourage everybody.
Highly recommend it. If people didn't see that, go back and watch the reruns.
Yeah, it's a good
Our
one.
taps are the wrong kind for water, guys.
Yeah, so actually, so in this case, if you actually plug in the frequency distance into the formula, the echo that was actually being reported was actually only about 12 feet in length. So even although Arnie was kind of like pointing out the fact that we had a drop, which was obviously way longer than 12 foot. I mean, the echo that was actually sort of like causing that reflection was actually sort of like much shorter that we actually had in there. And the other thing just to point out here as well is that problems like this, and we touched on this earlier, when we start looking at like self-installs, especially for people that maybe sort of like going into a home that already sort of like had a drop to the side of the house, can't necessarily point at an installer on this one. It may just simply be that a customer did a self-install, and without sort of like going back afterwards and sort of like doing a check, you can't really sort of like see some of these issues.
Yeah, fair enough. And like you said, when he removed that ground block connection, he did not see a standing wave. That connector interface could have been one side of the reflector that was causing the standing wave. And so just by simply removing it, could have not fixed it, but made the standing wave go away. So there's a lot to it, but spot on.